Good evening, everybody. Welcome to Chem 1105 with your host, me, Dr. White. Hi, everybody. Tonight I'll be doing a review for test number 3. But before I do that, there's a couple things I want to talk about. First of all, real quick, uh, public service announcement from the management, me, hand in your labs. Remember, there's a lab amnesty program. A number of you had problems getting your lab kit in a speedy fashion, so you fell behind. I'm giving you till December 1st to hand in labs 1 through 8. After that date, anybody who has to hand in labs 1 through 8 gets a 0. Labs are easy points. So hand in your labs. The other thing I want to talk about here, I have, remember this Thursday, the 16th, we'll be having test 3. I sent out this announcement about that. I sent out, put an announcement, you got an email, recommendation or advice. You should have watched these videos and do the practice problems for chapter 6 and 5, which is 5.5 for solutions. Also, for those of you, and some of you did have trouble with the math on test 2, where we're doing mole problems, you'll need to know how to do that for test 3. I'd highly recommend you watch part of this video. I think it's the second half. Always feel free to contact me or come to my office hours on Zoom if you have any questions, because remember, in my class, in my world, there's no such thing as a dumb question. Now, the other important thing I want to talk about before we get into the review is the extra credit project. And it's worth 10 points, bonus points. It's like getting another 10 points on a test. And where do you find it? Go to the assignment area of Blackboard, and you'll see it's right here. And if you click on this, you see I have both as a PDF file and as a Word document, and the other stuff I normally do, how to submit it. Well, let's take a look at this. And you'll see on your screen the extra credit project, 10 points. It's due by December 1st. No late projects are accepted, period. Now, one thing I should mention, this is an optional project. You don't have to do it. But if you'd like to get an additional 10 points, that can never hurt your grade. I would highly recommend it. Also, this is not a group project. You can't work with other people. That's called cheating. And I don't like that. That's one of the 2 things in life that get me upset. You don't want Dr. White upset. I don't want Dr. White upset. Now, how do you get your 10 points? Well, you create a table with a list of ionic and covalent molecules found in an ingredients list of products that you can purchase. i.e., by the way, that means shorthand in Latin for that is things you can use in your daily life. Now, you must find 5 different molecules that contain ionic bonds and 5 different molecules, this is important, that contain only covalent bonds. And you can only use 3 molecules from one product. So if you do the math, you should usually easily find 3 molecules per product. So you just got to look at 4 different products. If you want to do more, feel free to. Now, to get your 10 points, you must upload in a PDF file or a Microsoft Word file a table with the product's name, the molecule's name, and whether it's ionic or covalent. By the way, be sure to put your name on the table. You'll get 1 point for each correct entry, and it's a total of 10 points. Now, to make it interesting, you can't use gasoline, water, sodium bicarbonate, also known as baking powder, or baking soda. You can't use carbon dioxide, ethanol, also known as ethyl alcohol, milk, butter, vegetable oil, corn oil, olive oil, sugar, sodium chloride, also known as table salt, air, oxygen gas, nitrogen gas, or natural gas, which you cook with, which is also called methane. Anything else is free game. And how do you do it? Well, here's an example. You have a product column, molecule, bond type. And if you had Coca-Cola and you put down water, I can do it as an example, but you can't use that on yours. It's covalent. And if you had a can of Campbell's soup, you'll see on the ingredients label sodium chloride, and you know that's ionic. Now, ingredients must appear on an ingredients list on the product. You can't say a certain compound like an ester that's in a banana that makes it taste and smell like a banana, which is there. I've never seen an ingredient list on a banana. If you have, show me and I'll give you the points. No, you're not going to find it. Now, couple things. How do you know if it's ionic? If it has in the name of an alkali metal or an alkaline earth metal, it's going to be ionic, or any metal. So if it says sodium carbonate, well, as soon as you see the sodium, you know that's got ionic bond in it. Now, if it doesn't have that, most likely it's covalent. Now, let me show you an example. By the way, you can use this. Carmex, you know, with the winter coming on, this is great. I've been using it for many, many years. You put it on your lips in the winter when it gets real cold outside so it doesn't get chapped. And if you look on the label right here, one of the chemicals is phenol. So you could put Carmex, phenol, and that's covalent. There's your 1 point. See how nice I am? I just gave away 1 point. Boy, I shouldn't have been so nice. But anyways, there are 2 more you can get from here. So that's 3 and you need 7 more. Now, easy way to find stuff. 1, go in your bathroom and look at some of the things you have there. Mouthwash, toothpaste, you get this, even your bar soap. Or go into your kitchen, open up the refrigerator and look at some things with labels. Or open up your pantry and look at cans of stuff with labels. And that's how you do it. Now, as a public service to my students, you can use Google to find out if it's ionic or covalent, or you can ask me. Now, how do you ask me? Here's what I'm going to do. Before the project is due, send me your table by email. Don't upload it to Blackboard yet. I'll look at it. If something's wrong, I'll email back to you. You've got to change this. Like if you put down for sodium chloride, if you had that, which you can't use sodium chloride, if you'd put down covalent instead of it's ionic, I would write back, you know, the Campbell's soup sodium chloride, that's not covalent. Hint, I won't put down hint. Well, if it's not covalent, then you know to change that to ionic. Now, please count. If you only put in 8 things, you can't get 10 points. I've had students over the years, and I've been doing this for a while, because it makes you look at, wow, the stuff I use in my daily life have chemicals in them? Yep, they do. You forget water's a chemical too. It is. But anyways, they said, Dr. White, everything was right. How come I didn't get 10 points? Well, you only put down 7 things in your table and you need 10 things. If you're having any problems with this, email me or come to my office hour. All right. Let's get going with the review for test number 3 that's coming up this Thursday, the 16th. Now, what you see on the screen is a file called Chem 1105 test 3 review, and it's in the lecture section of Blackboard. I'm going to say so the wrong school computer system at ECC, Elgin Community College. It's called D2L, Desire to Learn. Blackboard's much better, but don't tell anybody I said that. All right, let's get to work. First of all, chapter 6 deals with gases. And when you measure, have a gas, an important thing you can measure is the pressure. And you should know, and this is a mistake here, it's correct on your test. .760 torr equals 760 millimeters of mercury equal 1 atm, which is called atmosphere. And those are the different units chemists use mainly for pressure. Now, in the real world, we also use PSI, pounds per square inch, like my car tires for my Ford Explorer. I keep at 35 PSI. That's the pressure of the gas inside my tires. Now, one of the things, as you've known, I've done all semester is cut down on memorization. And I'd highly recommend you go to, let me make sure you're seeing this. Yeah, hold on. To the lecture section of Blackboard, and you'll find the file important information, test number 3. And these will be on the last couple of pages of your test. It's like what I did for test 1 and 2 for those tests. If you notice here, I have it right. 760 torr equals 760 millimeters of mercury equal 1 atmosphere. Now, let's go to practice problems, chapter 6. Now, remember I talked long ago about watching the video, how to ride a bike? And if you just watch it, the first time you get on a bike, you fall off. I'm going to do one of these, but you should try these on your own. So let's look at number 4. How many torr is 1.237 atmospheres? So what do? Well, you've learned by now, write down what are you trying to find? Torr. What are you given? Atmospheres. Well, how do I convert atmospheres? What units do I want my answer? Torr. Well, if you had a ratio, what would be on top and bottom? And it's time to use your good buddy, your good friend, unit analysis. I love my little siren whistles, if you haven't figured that out by now. And for number 4, whatever we're trying to get to, the units go on top of that ratio. Whatever we're trying to get rid of, remember, anything divided by itself is number 1, goes underneath. And where do you find this relationship? Remember, if 2 things equal each other, there are 2 ratios. And important information, test number 3, we have 760 torr equal 1 atmosphere. These are all exact numbers because this is a straight definition. Therefore, 1 atmosphere equals 760 torr. Stephen wrote it up here. And 760 goes on top, 1 atmosphere goes underneath. Now, these are exact numbers. They play no role in significant figures. When you're multiplying, dividing, you get the same number of significant figures you multiply and divide, excluding exact numbers, as the number that you get the same number of significant figures in your answer as the number you multiply and divide in that problem. In this case, 1.237, 4 significant figures, oops, excuse me, exact numbers. Notice I got 4 significant figures. On test number 3, underneath your name, just like 2 and 1, it will say, please use proper significant figures for all calculated answers. It will also say, please use all atomic masses, the 3 significant figures. If you don't, I'll take off a point. So make sure you follow that. All right, let's get back to the review. Now, just to remind you, in gas problems, you don't use Celsius for the temperature, use Kelvin. And this is how you convert that. You learned that test 1. That formula is an important information. Test number 3. See, I've cut down the memorization. Thank you, Dr. White. You're welcome. Anyways, next, let's talk about Boyle's law. There's certain gas laws that help determine relationships between various parameters of gases in a sealed container or system. And as I mentioned in the videos, these were discovered during the Industrial Revolution because of the steam engine and the gasoline engine or combustion engine relies on gases expanding and contracting. And Boyle came up with this law, P1 times V1 equals P2 times V2. Now, P1 is the initial pressure. V1 is the initial volume. P2 is the final pressure, and V2 is the final volume. And they can be in any units. Now, if we go to important information, test number 3, notice right here, I give you Boyle's law. If you've taken Chem 1105 back in 2018 when I taught it, you'd be memorizing this. But I finally decided I should just test people's knowledge of chemistry, not their knowledge of chemistry, and also their memory. Thank you, Dr. White. You're welcome. So let's look at a problem using Boyle's law. And if we look at number 6 on chapter 6 problems, if a balloon has a pressure of 658 torr and a volume of 1.894 L, L is liters volume, what is the pressure of the balloon if the volume is increased to 5.133? Now, what are we being asked to find? A final pressure. After you do something, what's the pressure? And that's P2. P2, final pressure. You're given a balloon has a pressure, the initial pressure, P1, 658 torr. It has initial volume, 1.894 liters. And you're changing that volume to a final volume of 5.133 liters, V2. Now, if you notice, all you're dealing with is pressure and volume and a gas. Immediately, Boyle's law, P1 times V1 equals P2 times V2. Now, having written this out, by the way, if you haven't figured by now, I'm a proponent of let the paper do your thinking. Show all your work. It helps get a better score. 1, if you make a math error, I can give you partial credit. And 2, even when I was in grad school and in undergrad, somehow I figured out the more I write on the paper and the less I keep in my head, the better scores I got on tests because I didn't get confused. I highly recommend you do that. All right, so we have P1 times V1 equal P2 times V2. We want to solve for P2. We want it alone on one side. Well, anything divided by itself is number one, it's gone. So if I divide this side by V2, V2 divided by V2 is 1 times P2 is P2. But whatever you do to one side, you have to do the other. So I also divide the other side by V2. And now you have P1 times V1 divided by V2 equals P2. Now I like to do it. You don't have to. I just rewrote it so P2 is on the left. I have P2 equals P1 times V1 over V2. I have these numbers, so I can put in P1, I can put in V1, and I can put in V2. Now you still can use your good friend, your good buddy, unit analysis. Notice on the top I have liters, on the bottom I have liters. Anything divided by itself is gone, so I'm left with torr, which is a pressure, so I know I set it up right. Now, remember, when you're multiplying and dividing, you get the same number of significant figures in your answer as the number with the fewest significant figures you're multiplying and dividing. And here, 658 is 3, 1.894 is 4, and 5.133 is 4. So you have 3 and 4, which is a smaller number, and times up. Hopefully I'll pick 3, and you round what you have on your calculator to 3 significant figures. Now I didn't write it here, but it also could have been 2.42 times 10 squared torr. That's just having it in scientific notation. Now I have other ones for you to practice. Remember, I also have a folder in Blackboard where I have the problems without the answers. You should do that, and then you can go to the problem set here with the answers. All right, let's go back to the review. Now, next thing I talked about, now, Charles' law I briefly mentioned that will not be on test 3 or the final. Charles' law will not be on test 3 or the final. Everybody get the message? All right, let's talk about the ideal gas law. And the ideal gas law is PV equal nRT. And Dr. White loves the ideal gas law. It's my favorite mathematical formula in chemistry. Now you know I like chemistry. All right, now P is pressure, and it's always in atmospheres. V is volume, it's always in liters. N is the number of moles. T is temperature, it's always in Kelvin. And R is the universal gas law constant. And for this class, that's 0.0821 atmospheres liters per mole K. Now, R is a calculated number. Therefore, the one I use has 3 significant figures. Remember, R is 3 significant figures. Now, before we go here, it's time for another public service announcement. And that is PV equal nRT tells you when to check your car tires. If you watched the video, I talked about the time I walked out to my car when I lived in an apartment complex. And the night before, the temperature was minus 20 Fahrenheit, and that wasn't the wind chill. I figured, well, I better go out and start my car and drive it around. I looked like, oh no, I've got 4 flat tires. Then all of a sudden, it took about half a second, my brain kicked in, you're a chemist. It's cold gas, PV equal nRT. And I went to the gas station and filled them up with air. All right, remember, ideal gas law. In your car tires, the gas in your tires follows the ideal gas law. Now, hopefully you don't get a flat, but in your car tires, the volume doesn't change, the moles don't change, and the temperature, the universal gas law constant is a constant. That doesn't change. And coming up in winter, what happens? The temperature goes way down. Well, like that night when it was 20 below, I went out the next morning. If you have the ideal gas law, the temperature goes down and these stay the same, your pressure goes down, which is what happened to my car tires. So when it gets real cold out, keep an eye on your car tire pressure. Now, back in the summer of, I think it was 1995, we had a brutal summer. For almost 2 weeks, temperature never got, daytime temperature was above 100 every day for over 2 weeks. And I'm not talking about the feel, I'm talking about the thermometer temperature. And there again, PV equal nRT. What happens in the summer? Temperature goes up. And your tires, you've got gas, and V, N, and R are constant. If the temperature goes up, guess what happens to the pressure in your tires? It goes up. And at that time, I was living in the Schaumburg area, and I worked at a chemical pump company that was, let's see, northeast, about 10 minutes from Great America and Gurnee. That was a long commute. And on the toll road in the afternoon, you saw trucks and cars pulled over with their tires blown out. They didn't keep an eye on the pressure, the hot temperature from the air, and also driving on the pavement made their tire pressure increase and blow up like a balloon you blow up. So remember, PV equal nRT tells you in the winter, check your car tires because the pressure is going to go down if the temperature goes down. And in the summer, when the temperature goes up, guess what? Your pressure is going to go up. And what I did that summer, a couple of times, I checked my tires and I had to let some of the air out. Otherwise, I would have had a blowout. I didn't because I knew PV equal nRT. So this is the ideal gas law. Let's look at an ideal gas law problem. And again, this is chapter 6. Oh, let's do number 11. This looks fun. All right, a tire, ooh, we were just talking about tires, contains 25.67 grams of nitrogen gas, N2, at 26 degrees C and 705 torr. What is the volume of the tire gas, nitrogen gas in the tire? Oh, there's one thing missing from the problem. 15 points. Yep, this is a big one. 15 points because you got a lot of work to do. So let's take a look at this problem. What are we being asked to find? The volume, V. We're given the weight of the nitrogen. We're given the pressure. We're given the temperature. And 15 points. So immediately you should know PV equal nRT. Now, just as I've done, let's look in test number 3, important information. Here is PV equal nRT. And I also tell you pressures in atmospheres, volume in liters, N is the number of moles, temperatures in Kelvin, and the universal gas law constant is 0.821 atmospheres, liters, mole K. Well, here we have PV equal nRT. What do we want to solve for? V, the volume. So we want it alone on one side. Well, I have P times V. Well, if I divide P by P, that's the number 1 times V gives me V. So whatever I do to one side, divide by P, I have to do to the other. So I now know V equals nRT divided by P. Again, let me say that again, but first, this is thirsty work. PV equal nRT. Because I know if you notice here, I'm talking about a gas and nothing is changing. That's a good sign you're using PV equal nRT. Also 15 points. But anyways, how do I solve for V getting a loan? In order to get rid of P, which is multiplied times V, I divide this side by P. P divided by P is number 1, and you're left with V. But whatever you do to one side, you have to do to the other. So we now know V equals nRT divided by P. But these values have to be in the right unit. Now, what is N? N is the moles. Oh, shucks, we have grams. So first you have to, like you learned in test 2, convert grams to moles. I have grams here, and I want to go to moles. It's time to use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio, moles of nitrogen. Whatever I'm trying to get rid of, grams of nitrogen. Uh-oh, don't look. The 2 fell off after the N. If you see it, let me know. Anyways, that should be N2. And where do you find a relationship between moles of a compound and grams? Well, guess what? Even though you learned it for test number 2, notice important information. Test number 3, 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights. Now, nitrogen, and hold on, let me open it up. You look at the periodic table, nitrogen M, 14.007, rounding that off to 3 significant figures is 14.0. So 2 nitrogen times 2 times 14.0, 28.0, 1 mole, 28.0. 1 is an exact number, 4, 3, exact number. I get 3 significant figures, 0.917 moles of N2. Now, this is a multi-step calculation problem. And there's 2 ways of rounding off. Rounding off at each step, Dr. White's a round off at each step person, or wait until the end. And I calculate both ways for you because I'm not going to force you to do it my way. See what a nice person I am? And don't answer that. But anyways, I'll have that if there's different answers. And sometimes they are different answers. All right, so we got N. R is the universal gas law constant. In case you forgot, here it is, an important information. 0.0821 atmospheres liters mole K. Next, temperature. Or I have here temperature. Let's go to bottom here. Temperature has to be in Kelvin. Let's go back to important information, test number 3. Here, it's important that you're in the right units. And that's why this is a 15-point problem. There's a lot of work, but there's a lot of points too, which is a good thing. And so remember, common mistake students do is they'll use pressure and torr. No, you got to convert it to atmospheres. They use grams. No, you got to convert grams to moles. Temperatures, degrees C. No, you have to convert to Kelvin. And notice up here, I give you that formula how to do it. Kelvin equals degrees C plus 273. So let's go back. temperature in Kelvin, degrees C plus 273, that's 26 plus 273 is 299. Are we done? No, we have moles and R, universal gas law constant, temperature, and now we need pressure. Remember, pressure has to be in atmospheres for it to work in this problem. So I have 705 torr. I want to go to atmospheres. I have a ratio that can convert it, and I do. Whatever I'm trying to get rid of, or whatever I'm trying to get to, goes on top of the ratio when you use your good buddy, your good friend, unit analysis. And it's been my good buddy and good friend since my senior year in high school when I was taught that by Mr. Ernest Salners, who was the chemistry instructor and head of the Department of Science at my high school. Great teacher. I still remember his name decades old later. Great teacher. But anyways, back to this. Atmospheres goes on top, torr go underneath. Where do I find a relationship between atmospheres and torr? Important information, 760 torr equal 1 ATM atmosphere. Those are exact numbers. I put it in, 3 significant. My answer is 3 significant. Now, V volume we're trying to get, nRT divided by P. Here's N in the right units. Here's the universal gas law constant, which you get from important information test number 3. Here's the temperature in Kelvin. And here's the atmosphere, pressure in atmospheres. And moles cancel out, Kelvin cancel out, atmosphere, and you're left with liters. Hey, I did it right. And you get 24.3 liters. Notice I have both ways. And why do I say that? Because if you round off at the very end or at each step, you get the same number. Have you noticed I have some other problems, like if you burp so much CO2, but you never thought I'd get into burps in this class. Well, I do. But try these on your own. All right, next, Dalton's law of partial pressures. The total pressure of a mixture of gases is the sum of the partial pressures. And that's a straightforward problem. I'll let you look at the videos. Now, important thing, we talk about gases when you boil a liquid like water, which I'm going to assume all of you have seen water boil in a pot in a kitchen. I hope you have, unless you live a very sheltered life, like are super wealthy and have people doing that for you. You've seen it. Warning, warning, artwork from Dr. White. If you laugh so hard you break a rib, I'm not responsible. Yeah, I am. Here's a hot plate. On top of that is a beaker of water. When you heat it up, you'll see bubbles form and they'll rise to the surface. And inside that bubbles is water vapor, which is water in the gas form. And when it collapses, you'll have water vapor on top. When the pressure of the water vapor equals the atmospheric pressure, and you take the temperature, can I write thermometer any smaller? Maybe. But anyways, that's called the boiling point. And you should know, hint, you should know that The higher the altitude you go on the Earth, the lower the atmospheric pressure. You go up to the top of the Himalayas, the atmospheric pressure is a lot less here. And that's why people have trouble mountain climbing. They bring their own oxygen, or they have to get acclimated to the higher altitudes, less atmospheric pressure. And when that happens, the boiling point gets lower. If you watched the video, when I used to go to Denver, friends who used to live there who now moved elsewhere, if you cooked something in boiling water in Chicago, if they say cook noodles for 10 minutes, if you go to Denver, since you're mile high, higher than Chicago atmosphere altitude, the atmospheric pressure is lower and the boiling point of water is lower. So you got to cook it longer. All right, let's talk about solutions. Solutions are a mixture of two different chemicals, which neither one changes its chemical identity. In other words, a mixture is when you put two chemicals together and neither one changes its chemical identity. If I were to take and put sugar in my water, the sugar in there is still sugar, the water is still water. It hasn't reacted. Now, when it comes to solutions, important thing is you should know a solvent is the component of the solution present in the greatest amount. Again, a solvent is the component of the solution present in the greatest amount. All other components are solutes. So if I had 100 grams of water and put in 25 grams of sugar or salt, water would be the solvent, sugar or salt would be the solute. Now, water can also be the solute. Now, there's something that looks like a solution, but it's really called a colloidal dispersion. Those are particles of one substance suspended in some other substance. And how can you tell it's not a solution? It scatters light. I get to show off one of my fancy flashlights. This one's made by probably the premier flashlight maker in the world right now, Hank Wang out of China. I have a bunch of his. Those aren't him. I have about, and if there's sugar in here, this is a solution. If I were to take milk, a glass of milk, same light, you wouldn't see any light come through because milk is a colloidal dispersion. I better put away and see it's got fancy lights too inside, little, you can't see it well in this video. Anyways, I had my flashlight fun for tonight. But anyways, if you take milk or other things that are colloidal colloidal dispersions, mayonnaise, mustard, ketchup, the light won't go through it since the particles are not really dissolved, they're just suspended, they scatter the light. And examples I don't have here, but you should know milk is a colloidal dispersion. Latex paint is an example. And don't try this at home with a flashlight. Your blood is a colloidal dispersion. Your blood has, guess what? Fats and proteins and other things suspended in water. It's not a true solution. Now, next I talked about an important concept called like dissolved like. And like solutes are soluble in like solvents, which means polar solutes are soluble in polar solvents and nonpolar solutes are soluble in nonpolar solvents. If you mix polar and nonpolar, they separate. Just like oil and water, if you ever seen oil vinaigrette dressing. I don't have here, but let me just remind you, I did in my You should know water is polar, salts are polar, alcohols like ethanol or isopropyl alcohol are polar. Non-polar, vegetable oil, Vaseline, also known as petroleum jelly, gasoline. Let's see any others. Well, dirt and grease, but I'll talk about that later. But these are key ones. In fact, years ago, when I was teaching Chem 1211, which is a step up general chemistry at COD, a student of mine said, well, if like this sounds like is true, does that mean vegetable oil and Vaseline will be soluble in each other? I said, I don't know. Next time in our lab, I'll give you some. And do you mind doing it in front of the class? Said no. And he took a beaker. He put some vegetable oil that I gave him, put some Vaseline, mixed it, soluble. Why would you want to know that or do that? I don't know, but it does. One other thing I just thought of, baby oil. If you know baby oil, you put it on a baby's bottom to keep it dry because water won't get through it. Bet you never thought I'd get into baby's bottoms in this class. Well, I did. All right. Now, there's some certain definitions you should know. Solubility of a solute. That's the maximum amount of solute that will dissolve in a given amount of solvent. Now, there are different types of solutions. One is a saturated solution. That's the solution that contains the maximum amount of solute that can be dissolved under the conditions which the solution exists. That means it's totally saturated or full. You can't put any more. Dilute solution, there's a small amount of solute relative to the amount you could dissolve. Concentrated solution is a large amount of solute relative to the amount you could dissolve. An aqueous solution is a solution in which water is the solvent. And this is abbreviated in a formula by bracket AQ close bracket. And that means whenever you see this, water is the solvent. Now, when you're making solutions, you have a certain amount of solute and a certain amount of solvent. But how do you reproduce that? And that's concentration. And there are three different types. I'm only asking you to learn molarity, which is the most important for chemists. If you look on things you buy, you have concentration by percent weight, which a lot of things have that. Concentration by percent volume, that's mainly wine, but molarity is what we use. And molarity, which is designated by a capital M, you should know, is moles of solute per 1 liter solution. Well, 1 liter equals 1,000 milliliters. So it's moles of solute per 1,000 milliliters solution. Ooh, I even have very important, know this. You think you should know this for test 3? Yep. Now, let's look at some problems from chapter 5, part 5.5, solution practice problems. Well, give an example of colloidal dispersion. Well, I just talked about melt latex blood. Give an example of solution that you could use in your daily life. Well, Dr. White's from the Chicagoland area. We call that carbonated stuff in bottles and cans, pop. By the way, I'm a Verner's and Dr. Pepper person. I love Verner's. You've never had Verner's, go to local Jewel and get some. You'll love it. It's a real spicy, highly carbonated ginger ale. It's good. Air is a solution. Gasoline, tea. I love my tea from the Republic of Tea. And here I have, if you have a solution of 12 grams of KBR and 10 grams of water, what's the solvent? What's the solute? Solvent is the component present in the greatest amount. That's KBR. All other components, water, are the solute. Now, here I have what is 1.34 m HCl. HCl is the chemical formula for hydrochloric acid, and I'll teach you later in the chapter what that is. And capital M is molarity. And once again, let's go to important information. Test number 3. Molarity, which I didn't put the M in there on purpose, is moles of solute per 1,000 milliliters solution. So if we go back here, that means 1.34 moles of HCl per 1,000 milliliters. Now, if we look at number 7, what is 4.56 times 10 to the third capital M NaCl bracket AQ close bracket mean? And what is the solvent of the solution? Well, as soon as you see capital M, that's moles of solute, in this case NaCl, per 1,000 milliliters. In this case, it's 4.56 times 10 to the third moles of sodium chloride per 1,000 milliliters. Remember, capital M, molarity, moles of solute per 1,000 milliliters. And bracket, AQ close bracket, that always means aqueous, which tells you the solvent is water. All right, let's look at number 8. And I've got a few after this that are the same type. How many moles NaCl are in 125 milliliters of a 3.45 capital M NaCl solution? Well, by now you know the drill. What are you being asked to find? How many moles of sodium chloride? So I have question mark this. You're given 125 milliliters of solution. And you're given this number, 3.45 capital M NaCl. As soon as you see the capital M, that means molarity. In case you forgot, molarity is moles of solute per 1,000 milliliters. So immediately I'm going to write down underneath this 3.45 capital M NaCl. What does that mean? Remember, we just practiced that. 3.45 moles of NaCl per 1,000 milliliters. Now, the only number we really have to work with is 125 milliliters. So I'm going to start there. What units do I want my answer? Moles of sodium chloride. So whatever you're trying to, you put the units here, you're trying to get to moles of sodium chloride. And it's time to use your good buddy, your good friend, your analysis. I tell you early on, I was trying to go for the world record, saying your good buddy, your good friend, unit analysis most times a semester. I think I did. Whatever you're trying to get to goes on top of the ratio, moles of sodium chloride. Whatever you're trying to get rid of, milliliters, goes underneath. Where do I find that relationship? From the molarity. 3.45 moles of sodium chloride per 1,000 milliliters. And milliliters divided by milliliters cancels out, becomes number 1. I'm left with moles of sodium chloride. Now, listen carefully. When you're multiplying, dividing, you get the same number of significant figures in the answer. as the number with the fewest significant figures you're multiplying and dividing. Now, 125, 3 significant figures. 3.45, 3 significant figures. Now, the 1,000 is part of the definition, and therefore an exact number plays no role in determining significant figure 3, 3, and my answer is 3. All right, and I give you some more examples for you to try. Now, in chemistry labs, if you go to a COD, we're face-to-face in our stockroom, we have certain stock solutions, various molarities. How do you make those? And chemical plants, which I've worked at, you use large containers, like about 200 gallons we make up or more of stock solutions, so when we need it. Let's look at number 11. Oh, by the way, I forgot something there. 10 points. All right. How many grams, that's G, grams of sodium chloride are needed to make 345 milliliters of a 6.789 capital M NaCl solution? So you know the drill. What are you being asked to find? Grams of sodium chloride. That's why I put the question mark there. You're given how many milliliters, and you're given the molarity, 6.789 capital M NaCl. Remember, capital M tells you molarity, that's moles of solute per 1,000 milliliters of solution, which I write underneath, 6.789 moles of sodium chloride per 1,000 milliliters. Now, there's no way in one step I can go from milliliters to grams. There's no way I can go in one step from milliliters to grams. Well, what do? Well, in case you didn't watch the videos, you can go to important information, test number 3, and you have to do the 2-step molarity problem. Step 1, you convert milliliters to moles. Step 2, you convert moles to grams. So let's do that. Step 1, milliliters to moles. I have 345 milliliters. I want to go to moles of sodium chloride. It's time to use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio, moles of sodium chloride. Whatever I'm trying to get rid of goes underneath, milliliters. Where do I get these numbers? From the molarity, which means this, 6.789 moles of sodium chloride per 1,000 milliliters. Notice milliliters divided by milliliters cancel out. I'm left with moles of sodium chloride. Yay, that's what I want. And I do the math. Remember, use proper significant figures for all calculated answers. 3 significant for the 1,000 exact number doesn't play a role in calculating significant figures. When you multiply and divide, you get the same number of significant figures to answer. It's the number that has the fewest, in this case 3, and I have 3 significant figures, which I rounded off. Now, this is a 2-step problem. You can round off at each step, and I'm a round off at each step person, or you can wait till the end. I'll calculate both ways. Sometimes they're the same, sometimes they're different. What, am I done? No, I want to get the grams of sodium chloride. Now I'll do step 2, moles to grams. In case you forgot, remember that's in important information, test number 3. Thank you, Dr. White. You're welcome. And now I want to go from moles of sodium chloride to grams of sodium chloride. And what do? Well, if I have a ratio to convert to this, I use my good buddy, my good friend, unit analysis, Whatever I'm trying to get to, grams of sodium chloride, go on top. Whatever I'm trying to get rid of, I don't want mole in my answer, goes underneath. And where do I find a relationship of moles of something, of a compound, to grams of a compound? In case you forgot, it's important information. Test number one. 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights in grams. And if you go to your friendly neighborhood periodic table, sodium to 3 significant figures, 23.0. Remember, the number underneath the chemical symbol is the atomic weight, and chlorine is 35.5 to 3 significant figures. Remember, on test 3, it will say, please round off all atomic weights to 3 significant figures. And the molecular weight is the sum of all atomic weights, which is right here, 1 sodium, 1 chloride, that's 58.5. So I have 2.34 times 58.5 divided by 1 mole, 3. The 1 is an exact number. You get the same number of significant figures, and your answer is the number you multiply and divide. It has the smallest significant figures, which in this case both are 3, and that's how you do it. And if you notice, I give you some other examples for you to try on your own, which I highly recommend. And today being Tuesday, you got all tomorrow and a good part of Thursday, because I will be sending out the email with the password for test number. Hold on, let me make sure I finished everything. Wrong thing. Yep, I finished everything. Hold on 1 second. All right, with that, I'm done. Hopefully you've done the practice problems. If not, you have time, watch the videos again. You can always contact me by email if you have any help, any questions answered, or tomorrow night on Zoom at 7, I'll have my office hour. Come on by. Questions are always encouraged. With that, I'm done. And with that, I'll say, gang gesund. Remember, in Yiddish, that means going hell. And guess what? COVID's still out there. Just recently at the other school, one of my students there came down with COVID. That's online like this, but she got very sick. She's doing better now. I still wear my mask. In fact, let's see, last Friday, I got the newest Pfizer booster shot. Yes, I'm in a high-risk group, can't you tell? Well, with that, I'll say gang gesund. Goodbye. I stole that from Granny to Beverly Hillbillies. Bye.